Now we are ready to prove our theorem on the counting of number of n by n nilpotent matrices over a finite field. Let me state it as follows. So this is the theorem of Fine-Herstein. And the year is 1958. Let f sub q be a finite field of q elements and let nu sub n of fq denote the set of all n by n nilpotent matrices over fq. Then the cardinality of it is equal to q raised to the power n squared minus n. As a proof is due to Gerstenhaber. We'll prove this by induction on the sides of matrix n. If n is equal to 1, then the set of nilpotent n by n matrices, which is really the set of nilpotent numbers, will just be 0, because f sub q is a field. Any power of any non-zero number will be non-zero. So the only guy that is possibly nilpotent will be the 0 element. And the number of nilpotent matrices will just be 1. So this is a trivial case. And now assume for the induction hypothesis that Fine-Herstein's theorem is proved for all integers r less than n. So this is our induction hypothesis. Recall, by lemma 5, we have q raised to the power n minus 1 times this number we want is equal to the summation from r equal to 1 to n of m of r times the number of rank r admissible matrices, and by lemma 6, the number of rank r admissible matrices is equal to this product. What is unknown is this number m of r. We'll find this out using our induction hypothesis. To compute M of R, we look at the proof of lemma 5. In particular, we look at the end of the proof. At the end of the proof of lemma 5, we concluded that M of y is equal to M of this canonical matrix is rank R whenever y has rank R. So this tells you that M of R is equal to M of this block matrix IR 0, 0, 0, where this IR is the identity matrix R by R. And by definition, this guy is same as the number of nilpotent matrices A such that A nil commutes with this canonical matrix. And remember, this product is equal to just a block matrix NR 0, 0, 0. Now, for any matrix A in this set, let us study what A will look like. If A can be written as this block form, A1, A2, A3, A4, this is a block matrix, where A1 is R by R matrix, and A2 is R by N minus R, and A3 is N minus R by R, and A4 is N minus R by N minus R. Then this equation, let's denote this with star. Star is equivalent to NR 0, 0, 0 being equal to IR 0, 0, 0 times A1, A2, A3, A4. And if you compute this guy, this is just A1, A2, 0, 0 by the multiplication of block matrices. And this is further equivalent to saying that A1 is NR, while A2 is 0 by comparing both sides. Well, at the same time, A3 and A4 can be any matrices. Now for A equal to NR0, A3, A4, let us look at under what condition will A become nilpotent, so that we can find a necessary and sufficient condition for A to be in this set. And after that, we'll be able to count the number of such A's. So for A satisfying star equation, which is same as saying A has this form in terms of a block matrix, A raised to the power m will be equal to NR raised to the power m 0, A4 raised to the power m, and for this lower left block, we just put an asterisk in here. This could be complicated, but we don't have to worry about it. And you can see from here that A is nilpotent if and only if A4 is nilpotent. If A is nilpotent, then some power of A must vanish, which means some power of A4 must vanish. So this forward implication should be obvious. And if A4 is nilpotent, because NR is also nilpotent, just by its definition. So NR and N4 will both be nilpotent, and as a result, after you take certain powers, so this block and this block will both vanish. All that is left over is this star region, this star block. But this guy will also vanish if you take this m to be sufficiently large, because this is strictly off diagonal. So it follows that after you take certain power of A, this will vanish. That gives you the backward implication. I hope this is clear for you. You should have done such exercise when you learn linear algebra. So A is nilpotent if and only if A4 is nilpotent. Now we are ready to compute M of R. This number, the argument above, is equal to the number of n by n matrices over FQ such that A is taken this form, and R 0, A3, A4, where A4 is a nilpotent n minus R by n minus R matrix over FQ. Remember, A4 is nilpotent if and only if A is nilpotent. So to make A nilpotent, this is the only restriction for A3 and A4. For A3, we have full freedom of choices. And this number will be the product of the following two numbers. First, you want to count how many choices are there for A sub 3. Because A sub 3 has full freedom of choices, so this will be equal to the number of n minus R by R matrices over FQ. How about A4? As the number of choices for A4 will be just the number of nilpotent matrices of size n minus R by n minus R. And the first guy here is Q raised to the power n minus R times R. This should be obvious to you. And the second part. What is the second part? For the second part, we're going to use our induction hypothesis. By our induction hypothesis, the second part will be equal to q raised to the power n minus r squared minus n minus r whenever r is greater or equal to 1. If r is equal to 0, we don't know this number. But for r greater or equal to 1, namely the size of this matrix is less than or equal to n minus 1, we know this by our induction hypothesis. But we do have this condition because we are looking at the sum starting from r equal to 1. We are not starting from r equal to 0. So this is indeed true. And now we combine those two terms, which will give us q raised to the power n minus r times n minus 1. That is our computation of m of r under the induction hypothesis for r greater or equal to 1. And now with this knowledge of mr and our previous knowledge of a number of rank r admissible matrices. Sorry, this is a typo. It should be q raised to the power r minus 1, not n minus 1. So now let's compute the number of nilpotent matrices n by n over f sub q. So if you look at this equation, q raised to the power n minus 1 times the number of nilpotent n by n matrices over fq, which is the summation from r equal to 1 to n of the cardinality of a sub r times m of r. This will be equal to, so we look at this summation from the last term. We start with the term when r is equal to n. And for that term we get q raised to the power n minus 1 times q raised to the power n minus q all the way to q raised to the power n minus q raised to the power n minus 2 times q raised to the power n minus q raised to the power n minus 1. When r is equal to n, this guy will be simply 1. So times 1. So next term will be times, now when r is equal to n minus 1, when r is n minus 1, we get q raised to the power n minus 1. So this is q to the n minus 1. And the next term, all the way to q raised to the power n minus q raised to the power n minus 3 times, now when r is equal to n minus 2, we get q raised to the power 2 times n minus 1. Q to the power 2 times n minus 1. And we continue in this way. The last guy will be q raised to the power n minus 1 times, so do you notice the pattern here? The last guy will be when r is equal to 1. So it will be q raised to the power n minus 1 squared. This looks a little bit ugly, so let us move those terms to the left a little bit. So how do we calculate this? I'll let you think about it for a while, and I will tell you the answer later. The key observation for this calculation is that if you look at the first two terms, and if you look at this part, what do you see? You will see that this guy cancels with this guy. So the first two terms in this sum, when added up, will be equal to this guy. So this part comes from the blue box on the left. And now we copy everything else down in here. Next, you're going to look at the sum of the first two terms and the third term. In particular, you're going to look at this part and this part. So what do you see? If you still don't see it, let me move this guy to the right a little bit. So the term before it will be q raised to the power n minus q raised to the power n minus 3. And I told you to look at this part. When you add up those two parts, you will get that this part cancels with this product. It's negative q raised to the power n minus 2 times q raised to the power n. So this gives you, in the end, q raised to the power 2n. Previously, in this blue box, you get q raised to the power n. And now the calculation in the second step tells you, you get this tail part added up to be q raised to the power 2n. And you probably have already noticed the pattern. So you will continue this procedure. In the end, you're going to get q raised to the power n minus 1 times, for the last term, you're going to replace this 1 before n and 2 before n by n minus 1 before n. And when you simplify this, it precisely gives you q raised to the power n minus 1 times q raised to the power n squared minus n. And now, you divide both sides by q raised to the power n minus 1, which finally gives us the number of nilpotent n by n matrices over fq equal to q raised to the power n squared minus n. And that is the end of the proof. This proof is very elementary and beautiful. The only weakness, in my opinion, is that maybe you have to know this formula for the number of n by n nilpotent matrices over fq at the beginning, because we use the induction to prove this result. If you don't know this formula, it will be difficult for you to give this counting starting from scratch. Maybe you can use some special values for q and n to get speculations of this formula. That might be a possible choice. You try to guess it first, and then you prove it by induction. And I hope you enjoyed this video.